And here we are having to face the dreadful piece of paper with numbers on it. I have computed measured the series resistance of these inductors. Okay, let's start to make a few measurements of the resistance, the parasitic resistance in the inductors. We reset this to 0 to 0. Well, apparently that is as good as it gets. And now we can measure the resistance. Of the bigger inductor. This is 330 microhenries. That's, let's say, 1.8. It's a bit fluctuating. Let's try it better. .78 ohms. The other one, let's see. This is the 68 microhenry. 0.72. Okay. Now, don't pay attention to this. That is required to measure the current. It doesn't change the ring a lot. We have an inductor of 330 microhenries plus minus 10%. I measure the internal resistance to be about 1.84 ohms. The other side, the small inductor has an inductance of 68 microhenries plus or minus 10%, and an internal resistance of 0.72 ohms. The value of the inductance is on the low side. From some small measurement I've done, they turn out to be about 61 microhenries this one, and 290 microhenries this one. It turns out it does not change much the computation and the measurement, because they are both on the low side, and the voltages will be almost equal to what is predicted by theory that will come to this. There is not much to be said. We compute the impedance with the biggest inductor, internal resistance, reactance, and we get a value that is not 90 degrees because of the parasitic resistance inside. The same goes for the smallest one. Once we have these values as complex values, we can compute the current in the ring, which is the same for both resistors. It turns out it is about 10 milliamps, and it is lagging the voltage, the EMF. This is not exactly a precise graph, but well, whatever. I have scaled the values by square root 2, because when I made the simulations, I wanted to see the value as a peak and not have to compute it by measuring the actual RMS value. And what we got is just a simple RL circuit, which is more L than R because the resistances are kind of small. This argon diagram is not to scale, of course, but it shows that both VL and VH are out of phase with respect to the EMF. Their peak values or the RMS values do not adapt to the value of the EMF, but this is just normal circuit theory, nothing new here. The plus and minus signs on this drawing just remind me of the positive convention for voltages and currents. We have to imagine the voltages and the currents going back and forth between positive and negative values. And that's it. What we predict is 9.93 milliamp for the current. I will show that this is what we get in when we measure it using this sensing resistor. It's a 1 ohm resistor, and it gives more or less the value we expect. And the voltages, the RMS 84.3 millivolt RMS, and where is it? 18.4 millivolts are basically what we have measured with the voltmeters and with the scope. This is the scope with the 1 ohm resistor, and we're not far off. There is just a little bit of discrepancies due to the added 1 ohm resistor. Okay, one last thing. When I simulated the circuit, I used the nominal value of 330 microhenries for the big one and 68 microhenries for the small one, but they resulted a little bit less than that when measured. And now this is the simulation with, let me see if I can get it. Almost there. Okay, simulation with the nominal values, and I get about 18.5 and 84.3, which are more or less what we see here. Okay. While, let me see if I can point to this. While when I use the actual values, 61 microhenries and what was it, 290 microhenries for the inductors, I got 83.8, 18.9. The only notable difference was the current that came out a little bit higher at 11.2 milliamps. All measurements are RMS, but the simulations are scaled by square root 2 because I want to see the value as peak values. It's easier to see on the graph and not having to include measurement inside the simulation. And that's it. That's a good agreement with theory.